Show that x plus natural log of x equals 0 has a solution between 0 and 1 using the intermediate value theorem. So for this problem, what we want to do is first remember what the intermediate value theorem is and what it tells us. Basically what it tells us is that if a function is continuous on the interval from a to b, so from a to b, and I'm choosing these points arbitrarily, then the y-coordinate of a must be f of a, right? And the y-coordinate of b must be f of b. That if the function is continuous, in order for the graph to pass some point in between f of a and f of b at f of c, in order for it to cross that, there must be at least one value c where the graph will pass through f of c, at least. So maybe the graph looks like this, and this is kind of arbitrary. So in order for the graph to go through that point, actually past this line, to take on a y value of f of c, there must be some value c that makes that true. Now there could be more than one value c if the function goes up and then down and up and then down. There could be c, d, e, and f, all of which make it pass through that line. But if the function is continuous, it has to somehow get from a to b. There's got to be at least one value that you could put in where what you get out would be between f of a and f of b. So that's the idea behind the intermediate value theorem. Hopefully we can use this problem as an example to demonstrate that a bit more specifically. So the basic approach here is to choose, we know that the solution is supposed to be a value that x is going to take on that's between 0 and 1, where f of 0 is going to be less than f of x, which is less than f of b. So let's write that. So this function is our f of x. F of x equals x plus ln x. And now it's kind of hard to graph because we may know how to graph the natural log and we may know how to graph y equals x, but x plus ln x is probably some hybrid of the two. So if you're not using a graphing calculator, that may not be immediately obvious to you. So let's just realize where it's defined. Its domain of x is all real numbers. Domain of ln x is all positive numbers. And if you need to go back and review the natural log function, that may be helpful. But let's realize that this function is continuous. On the interval of x is for all positive values of x, right? So the natural log is not defined at 0, and it's not defined for negative numbers. You can't take the natural log of a negative number, so it's only defined for positive values of x. And now we want to say that c is some value between 0 and 1, because we want to show that there is a value of c that's between 0 and 1 that will make f of x equals 0. So that's what we're hoping to show. So what we'll do is we'll take f of 0, and hopefully that's less than f of c, which is less than f of 1. So this is our game plan. We believe that f of 0 is going to be smaller, hopefully it's going to be negative, and f of 1 is going to be positive. So then there must be some value c that can make f of c 0. That's the game plan. But what's the problem? The problem is we can't take f of 0. We just said that the function f of x doesn't have 0 in its domain. So we can't find this. f of 0 is undefined. So what we can do instead is we can just choose a small number. It won't be 0, but it'll be just a small number. So, and we're going to have to take the natural log here when we actually find f of that number. So we might as well choose something that's small but is going to tie in nicely with the natural log of x. So for convenience, I'm going to propose that we change this and make it 1 over e. So e is like 2.71, right? So 1 over 2.71 is a little more than a third. So it's still a pretty small number. Is hopefully less than f of c, which is less than f of 1. Now we don't know for sure that this is going to work. It could be that, oh, I wrote f of, sorry about that. At this stage I don't want to write that just yet. I want to write 1 over e is less than c is less than 1. And then we'll take f of each of those. Now, this could backfire because the value of c that makes the equation true could be between 0 and 1 over e. But I'm pretty sure that 1 over e is sufficiently small that we're going to find out the value is between 1 over e and 1. So now we're ready to say f of 1 over e is less than f of c, we hope, which is less than f of 1. And now I'm going to jump up here and actually make those substitutions. So what's f of 1 over e? We're substituting in here now. Wherever we see x, we'll plug in what we're finding. So for x, we write 1 over e plus the natural log of 1 over e, which is less than f of c, which is less than f of 1. f of 1 is 1 plus ln 1. Well, what is the natural log of 1? Well, hang on. Let's start from the left. So 1 over e, we can't simplify. Natural log of 1 over e is the same as natural log of e to the negative 1. And the natural log and e are inverse functions. So this just becomes negative 1. So it's 1 over e minus 1. And that's less than f of c, which is less than 1 plus natural log of 1. Natural log of 1 is 0. So this is just 1. So what have we shown here? Well, what we're saying, 1 over e is a small number, minus 1 is definitely negative, right? So without even finding out exactly what this is, let's just recognize for a minute that this is negative. And that's less than f of c, which is less than 1, which is positive, right? So f of c has a value of 0, a solution, right? Because this is our f of x, and we're saying it equals 0. So when f of c equals 0, it's between a negative and a positive, right? So there must be a value of c that will make this equation true, for which c is between 1 over e and 1. And if c is between 1 over e and 1, can't we also say that c is most certainly between 0 and 1? Absolutely, because all the values between 1 over e and 1 are certainly between 0 and 1, because this is more restrictive than that. So that's the proof. We can say there must be a value of c. c exists such that 1 over e is less than c is less than 1, which implies, I don't know exactly how we want to write this. This is not the most formal way to write this, but I'm hoping that it just makes some sense, that clearly 0 must be less than c is less than 1, because 0 is less than 1 over e. So hopefully that helped, and hopefully this makes sense too. I want you to really understand the graphical version of this, that if the function has to somehow get from a to b, and f of a is less than f of b, and the function's continuous, I hope it's relatively obvious to you that there has to be some value of c that's going to make the graph cross that line at least once along the way, at least once on that path. It could cross many times. And it doesn't necessarily mean we have to find out what that value is. We just have to prove that there is such a value on that interval.